In this video, I now present to you the fourth case, a case where the exponential term we have in this f of x happens to be a part of the complementary function obtained by solving the homogeneous part of this non-homogeneous SOODE. You know, the homogeneous part is a 2y d squared x plus b dy dx plus cy equal to what? 0. When you solve, you obtain a solution there which we refer to as a complementary function. Now you notice that the exponential term in this f of x forms part of that complementary function. In this case 4, it is not only that the exponential term in this f of x forms part of this complementary function, but the exponential term in that f of x is multiplied by another function. Now, the function here, p of x, could be a polynomial. Generally a polynomial, alright? But because of what we saw in case 1, 2, 3, I have decided to assume that this p of x can also be a constant. So I'm looking at the possibility of it being a constant so that we could do something. Because my interest is to see how we can generate a formula which we can use to solve all cases, case 1 to case 4, no matter what it is. So that we would not start stressing ourselves thinking of, okay, this is the YP form of this is the YP form. If it's like, you know, I want us to get something that can handle all problems for us, which if we are to think of maybe the particular integral form, it will not be the standard that was introduced from the outset of our studying non-homogeneous SOODE. Is that okay? So based on that, I've considered the possibility that okay, this p of x could also be a constant. If you take your mind back to case 1, 2, 3, you notice that the f of x part, alright, the exponential term there was multiplied by k in case 1, 2, 3, where that k there represents what? A constant. And so it is based on that fact that I have taken the assumption that p of x should be either a polynomial or a constant. Now, when we have a situation like this, how do we handle the particular integral part which gives us the solution of f of x? When you have two functions being multiplied, where one of them is an exponential function. Is that okay? So this is what we do. We have to get the particular integral of this p of x. We have to get the particular integral of this exponential term, and then we multiply both of them to give us the general particular integral of this f of x. That is what I showed by equation 4 here, that the particular integral of our f of x in this case is equal to y sub p sub 1 times y sub p sub 2. Where y sub p sub 1, I've taken it to represent the yp of the p of x, the function called p of x, which like I said could be a polynomial or supposedly a constant. And then I am using y sub p sub 2 to be the yp, the particular integral of the exponential term there. So once I know the particular integral of this, the particular integral of this, multiply both of them. Now, going by the general format of approaching a non-homogeneous second order ordinary differential equation, having known the particular integral of this function, look at this, a product term. You know now that you have to differentiate how many times? 2 times, because this is a second order ordinary differential equation. This and this are still the same thing, the prime concept of differentiation. So I will differentiate this yp 2 times. The second derivative I'll substitute it here. The first derivative I'll substitute it here for the y prime. And then the yp itself will now take the position of this what? Y. Once I substitute them into the given non-homogeneous SOODE, make it equal to p of x times exponential alpha x. The next thing is simply to work it out, alright, and then get my result. But the truth is, it is not just that simple, like I've said it, you know, because in the first case, take note of this, you are multiplying y sub p sub 1 by y sub p sub 2. Ordinarily, to solve this, you need to use product what? Rule to differentiate this. This is not even to talk of what the yp sub 1 and yp sub 2 may be. Because the function that thing assumes determines how fast you can differentiate it. And that is why, to make this process quite easy for us, to ensure that we use a particular format in approaching all questions, all the cases, irrespective of whether it is an exponential term multiplying a polynomial term, or whether it is a constant multiplying an exponential term, or whether the exponential term in the f of x appears in the complementary function. Whatever the case might be, I have decided to work out something that could be of interest and help us handle the problem with ease. And that is why, at this point, I am delighted, I take the exquisite delight in presenting to you the OMAKA's legendary formula. And that we have on the board here. Now, with the OMAKA's legendary formula, you can solve any of the 4 cases in a similar way, without stress, without thinking what is the particular integral of this function. Okay, this exponential term in the f of x appeared in the complementary function, so what do I do? You really don't need to stress yourself on that anymore. What is the OMAKA's legendary formula all about? Please come along with me as we go through the analysis of it on the board here. Now, just imagine you're given ay prime prime plus by prime plus cy equal to f of x. It's the same as a d2y d squared x plus b dy dx plus cy equal to f of x, such that f of x is equal to p of x times exponential alpha x. You see now, right, that the f of x now contains the polynomial function or a constant times the exponential function. Are you following? And now, p of x is not equal to 0. It's not equal to 0. Alpha is a constant. We can use a particular concept to approach the particular integral of this f of x, of this. Instead of going by thinking of what is the particular integral of p of x, what is the particular integral of the exponential term, so that we multiply through this way, and then start thinking of using product rule. Instead of doing that, we go straight with this. That the particular integral of such term is given as y sub p equal to v sub p exponential alpha x, where the exponential alpha x is already the exponential alpha x in the f of x. With this, our problem is simply to obtain the value of what? The v sub p. Our problem is to obtain the value of what? V sub p. Once I know v sub p, which is another form of particular integral that I introduced, once I'm able to solve for it and get a value, I'll just simply substitute it here, and then I'll get the particular integral of this f of x. Are you following, right? And then I'll smile. Now, what's going to help us do that? The OMAKA's legendary formula. It can help us to easily obtain the value of that v sub p. And here we have this OMAKA's legendary formula on the board, given by the equation which I've labeled the OLF, O-L-F, OMAKA's legendary formula. And it goes, A v prime prime plus A prime alpha of v prime plus A of alpha v will be equal to P of x. Will be equal to this P of x. So you need to memorize this formula. This is what I refer to as the OMAKA's legendary formula. What's the meaning of these terms used here? A, small letter a here represents the coefficient of the second order derivative of y in the given non-homogeneous SOODE. V, of course, represents what we're trying to get, the v sub p. Is that okay? Now, you have it as v prime prime, so it means we're going to differentiate twice. Are you following? And then plus a prime. This a prime means the first order derivative of a. And what is a? A happens to be the auxiliary equation am squared plus bm plus c of the differential equation part here. That is ay prime prime plus by prime plus cy. You know already from what we studied or we learned from homogeneous SOODE, you can always get an auxiliary equation from any given second order ordinary differential equation. So this A here represents that auxiliary equation. Are you following, right? Obtained from this part. You can say that here. Obtained from it. Now, the a I've stated that is the coefficient of y prime prime, which of course if you're taking it from the auxiliary equation, it is the coefficient of m squared. Alpha is the coefficient of x in the exponential alpha x. I hope I'm communicating. Now, why did we get something like a prime of alpha? This simply tells you, go to the auxiliary equation. I've already told you that this capital letter A represents the auxiliary equation. So a prime here means first derivative of the auxiliary equation. So you are going to differentiate this auxiliary equation once to get this term. Are you following, right? And then this alpha is telling you to substitute alpha for n. Look at the alpha, the quotient of x in this exponential term. Once you differentiate the auxiliary equation once for this term, you fix in alpha for n, simplify it to give you this value. The v prime will remain there. This v prime will also remain there, right? Then come over here, plus a. Our a is the auxiliary equation. So a of alpha simply tells you, go to the auxiliary equation, wherever you see n, fix the value alpha into it. You get a number, you multiply by v, then make it equal to p of x. Where p of x, like I stated initially, can either be a polynomial or what? A constant. Is that okay? Now, having explained this term, it's absolutely necessary that you memorize this OMAKA's legendary formula. In the next video, we are going to see how this OMAKA's legendary formula, the form it can take if this p of x is taken into consideration in terms of the degree. That's in the case where p of x is not a polynomial. We now talk about the degree and then compare whether this first term exists in this OMAKA's legendary formula or whether it does not exist. Also, whether this second term appears in the OMAKA's legendary formula or whether it does not. Of course, this term av prime prime must always be there. What I just said here is based on the fact that we have case 1, case 2, case 3. Case 1, where the exponential term, in the f of x here, does not appear in the complementary function you obtain by solving this homogeneous part. Case 2, when this exponential term appears, if the exponential term in the f of x appears in the complementary function, then coming to this OMAKA's legendary formula, this first term will not be there. So I'm going to isolate those cases in the next video. And then, in a case where the exponential term in this f of x appears twice, 2 times in the complementary function, then this first term and this second term, which is the first term you didn't differentiate v there, and then this second term where you had the first derivative of v, these 2 terms will not be there in the OMAKA's legendary formula, making the case even quite much more simpler. In the next video, I shall introduce these cases and then we'll now pick questions to see how we apply this OMAKA's legendary formula in full. Having formally and successfully introduced the OMAKA's legendary formula, it is now time we want to look into the application of the OMAKA's legendary formula OLF to the 4 cases that we've been treating. Remember the 4 cases. Case 1, when the exponential term in the f of x of the non-homogeneous SOODE does not appear in the complementary function of that non-homogeneous SOODE. Case 2, when the exponential term in the f of x of the non-homogeneous SOODE appears once in the complementary function. Case 3, when the exponential term in the f of x of the non-homogeneous SOODE appears this time 2 times, that is twice, in the given complementary function that you obtained. And then case 4, when you have a product term as your f of x such that you have an exponential function multiplying a polynomial function. Does that make sense? Something like this. Because when we get to that case 4, we will still break that case 4 into 3 sub-cases following our case 1, 2, 3. Does that make sense? So let us start with case 1. So you have this, you can go through that, exponential alpha x not part of the complementary function. Now going by the OMAKA's legendary formula, OLF, the legendary formula is going to take this form. You can see it contains all the terms. So go through it. AV prime prime plus A prime alpha V prime plus A alpha V equal to P of X, where in this case 1, P of X is a constant. So you can quickly take your mind back to our case 1. Is that okay? So in this case, P of X is a constant. So do you see now that all the terms in the OMAKA's legendary formula would have to be used in order to solve the problem? Now let us move on to case 2, where the exponential alpha x term in the f of x is part of the complementary function. That is, it appears in the complementary function once. Now going by the OLF, OMAKA's legendary formula, this is what we're going to get. Now you now take note that the A alpha V term no longer exists in the OMAKA's legendary formula. So what we're going to get is AV prime prime plus A prime alpha V prime equal to P of X. Once again, P of X in this case is a constant. You can quickly revisit our case 2 from the beginning of this lesson, alright? Now let's move on to the next case, case 3. This is a case where exponential alpha x and x exponential alpha x are part of the complementary function. What does that mean? Simply telling us that the exponential function or term in the f of x of the non-homogeneous SOODE appears 2 times in the complementary function. Going by the OMAKA's legendary formula OLF, the formula is going to take the form AV prime prime equal to P of X. And once again, our P of X here is a constant. I'm sorry that I have to still write it as a function of X. I explained the reason from the previous case when I formally introduced the OMAKA's legendary formula. Is that okay? So we're taking P of X to either be a polynomial function or in some cases it's going to be a constant. Is that okay? That's the assumption, the possibility I considered. Now let us look at case 4, where in that case P of X is no longer a constant. It's purely a polynomial of nth degree, that is degree n. Now in that case, for the f of x is no longer an exponential function multiplied by a constant. But in this case, the constant P of x, like I said, is a polynomial of a given degree n, where the degree is greater than what? 0. What will the OMAKA's legendary formula look like? What form will it take? Like I stated previously, we are now going to bounce back, applying this case 4 to the first 3 cases. Are you ready? That's why I have A. In this A, it means that exponential alpha x, which is this term, is not part of the complementary function you are going to obtain by solving this homogeneous part when it is equal to 0. Are you following, right? It is not part of the complementary function in this case. Take note here, P of x is a polynomial, is that not so? Now, if that is the case, it means that all the 3 terms in the OMAKA's legendary formula will be there, made equal to P of x, where of course, as I stated from here, P of x this time around is a polynomial, no longer what? A constant. So it seemed like the same formula in this case 1 applies. Is that okay? The only difference between this and this is that in this first case, case 1, the P of x is a constant. But in this case, where P of x is a polynomial, then you notice that what we're going to put here is a polynomial as would be given from the question. We move on, looking at this. Now, once this is the case, knowing that this is a polynomial, we need to generate the standard particular integral form of this polynomial P of x. And that is why we now have to seek for the value of what? V of P. You recall that the general particular integral in this case is V subscript P exponential alpha x. In the previous video, I wrote that. Is that okay? So we need to get our VP considering the degree of this polynomial. And in that case, it's going to be Cx raised to the power n plus Dx raised to the power n minus 1 plus, it can continue, Ex raised to the power n minus 2 plus let's say fx raised to power n minus 3, it goes on until you get to some constant times x raised to power 0. Once you reach that constant, I've chosen to use w for it. Is that okay? That is wx raised to power what? 0. That will be the form that the particular integral respecting the degree of this polynomial with respect to the OMAKA's legendary formula, this is the form in which the VP will take. And the reason why it goes in this form, take note I stated here that the degree of the polynomial is n. You notice the form that the VP took. The highest degree here is also what? Degree n. You can say that. Then the degree starts reducing by 1, 1, 1 until you get to a constant. So once you do that, you differentiate and substitute into this OMAKA's legendary formula and solve to obtain your VP. We're going to see this in practice when we solve questions. Is that okay? Now, we look at B part of case 4. That is in a situation where the first term of the OMAKA's legendary formula is no longer there, just like you have in case 2 here. Are you following, right? Once again, the difference between this case 2 and then case 4b is that this p of x in case 4b is a polynomial, but in case 2, the p of x is a constant. The same condition applies that you have a situation where the exponential function or the exponential term in f of x appears once in the complementary function. When that is the case, this formula applies. The OMAKA's legendary formula takes the form a v prime prime plus a prime of alpha v prime equal to p of x. We are to now get our vp. Is that okay? That's the particular integral in terms of v. Considering the degree of this polynomial, we'll now take the form cx raised to power n plus 1 plus dx raised to power n plus ex raised to power n minus 1 plus continuously down to some constant you choose to use. Did you take note of something here with respect to the degree of this polynomial? I stated previously that the degree of the polynomial is what? N. You took note of the form in which the particular integral took here, right? That the first term, the degree is 1 greater than the degree of what? This polynomial. So which means that if this polynomial is degree 2, let's assume maybe x raised to power 2 plus 5x minus 3. The highest degree there is 2. It therefore means that if the exponential term in f of x appears in the given or the complementary function that you obtained, now the formula, OMAKA's legendary formula, will take this form. The VP you are going to form will become cx raised to power 3 plus dx raised to power 2. Is that okay? It continues in that form down to, please let me make a correction here. This will stop at wx. It's not going to have a constant in that case. Are you following? Right? Okay, that's this term. It's not going to have a constant in that case. It means that the power, the degree of the polynomial in VP you're going to form will start from a degree which is 1 greater than the degree of p of x. It will now start reducing until it gets to a constant times x raised to power 1. You stop. It is in case 1 here, that is 4a here, that I have to get towards a constant. Because the exponential term in f of x did not appear in the complementary function. But whereby the exponential term appears once, the OMAKA legendary formula reduces to this, and then the VP is obtained from something like this. Is that okay? Where it stops at wx. Finally, 4c, case 4c. That case 4c goes in line with case 3. And once again, the difference is that in case 3, the p of x is a constant, while in case 4c, the p of x there is a polynomial. You notice now that the a alpha v term is no longer there. A prime alpha v prime is no longer there. What you have there is simply a v prime prime equal to p of x. So to obtain the value of your vp, all you need to do is 1 divided by p of x, kind of making vp subject of the formula. Then you take the integral of this polynomial twice. You know, the first integral will reduce this v prime prime to first derivative. Then the second integral will now reduce that first derivative to the function vp itself. That's why I have double integral of p of x dx. And that is all about the OMAKA's legendary formula. Take note, the same thing applies here. I follow you. You need to integrate to get a result in this case as well too. I think it's now time we are set to solve questions. We're going to solve questions so you see how swift one can use the OMAKA's legendary formula to solve problems that involves non-homogeneous second order ordinary differential equations. SOODE.